There's a movie where a young lad named Luigi puts a rat on his head and then becomes a vessel for creating outstanding cuisine in Paris. Well, wanting to become something of a rat chef myself, I sat my good friend Keith onto my noggin, and together we cooked up a Fibonacci number generator. Anyway, instead of blowing people away, I ended up blowing my leg off. What was supposed to be a fun exercise to implement the fast Fourier transform ended up costing me my leg, and of course it became my most popular video to date. Besides the inevitable comments rightfully calling me trash at C++, other people took the Fibonacci series as an opportunity to dog on C++ itself. People with oxygen rashes came out of the water to tell me to use Rust, this being the inevitable result when someone uses C++ nowadays. When I opted to just go old school and use C in subsequent videos, Will Smith came up and slapped me in the face, telling me to get ziggy with it. This being the inevitable result when someone uses C nowadays. If you laughed when I called C old school, you were probably one of the bare metalheads who told me I should have just written in assembly directly. There were probably some people also telling me to use Haskell as well, since I'm a category theorist or something. But my C++ code was already slow, I didn't want to make it slower. It's clear that when it comes to writing efficient software, every programmer and their pet duck has an opinion of why their preferred tool is the best tool for the job. Well, there's a new tantalizing sequence of numbers that I want to try my hand at computing, so I've given a lot of thought to everyone's comments and suggestions, and I think I've come to a language decision that will make everyone equally unhappy. Don't get me wrong, I actually love C++, even if it's probably a Stockholm thing. It lets me do whatever I want, no matter how cursed my idea might be. I also love C, because it forces me to be a better programmer. And you know what? I like writing in Rust. Yeah, I said it. I don't know why it gets a lot of hate. Maybe it's a culture thing, I don't know. On the other side of the spectrum, I definitely see the potential in Zig. But I'm not Leonardo DiCaprio, so I'll wait until the language gets a little older. Anyway, I'm not going to use any of these languages. And no, I'm not going to use assembly either. Yes, that is a skill issue. What will I be using then? Well, I think it's better to show than to tell. Although I have my sights on a much more interesting sequence, and my original plan was to get right into the thick of it in today's video, we're just going to write a simple program that takes a non-negative decimal integer from the command line and spits out its square, modulo 18,446,744,743,709,551,616. The entry point, as usual, is a main function. As one might expect from C-like languages, the main function returns an integer and can take arguments telling us about any command line arguments. Specifically, argc is an integer giving us the argument count, and argv is a pointer to the array of string values of each command line argument. In our case, we expect a single integer as the command line argument, which means argc should be 2. So, let's just check that argc is indeed exactly equal to 2 using the integer compare equals instruction. If we do have that single argument, then we'll compute the square. Otherwise, let's error out. We manage this control flow logic with the conditional branch instruction. The first label tells us where to branch to if the hasInt boolean is true, and the second is where to branch to if hasInt is false. Unfortunately, like most languages, this language also assumes the law of the excluded middle.
Hell no, to the no, no, no.
Let's look at the error path first, since it's simpler. All we're going to do is print an error message and then exit main with a return code of 1. We print an error message with the puts function, which we declare to indicate that this function is defined in a different file. As for the error message itself, we'll define it as a private global string constant. Don't forget the null terminator, or else puts will start printing garbage. That handles the error path. As for the main execution path, we need to parse the command line integer. This means first getting the string representation of the input, which is held in argv. We can do this with the incredibly intuitive getElementPointer instruction. In our specific case, getElementPointer is calculating the offset from the base pointer argv to element 1, assuming every element is the size of a pointer. In other words, we're computing the address of the first index of argv viewed as an array of pointers. Once we have this pointer, we need to dereference it to get the pointer to the actual null-terminated string holding the integer we're interested in. We convert the string into an integer with the string to unsigned long function. With that, we finally have our input integer x. We can easily compute its square using the multiply instruction. And then finally, to print the integer to the console, we need to use our good friend printf. If you've interfaced with printf before, then you know how to print a 64-bit unsigned integer. We don't have a convenient /n escape sequence for the newline character, but the newline character has an integer value of 10. As with our other string, don't forget the null terminator. Et voila! A complete program written in LLVM-IR. To compile our program, well, we need a compiler first. Not to worry, LLVM is an open source project, so we can just build it ourselves. This looks like it's going to take a while. You might want to do something else in the meantime, like read a book, or ponder life's greatest questions, such as, why do we exist just to suffer? Or, how can people sleep at night believing that there is a basis for the real numbers as a rational vector space? There's a demo for a cool new game called Blocking Blocks that's out, so I'll just play that. The guy who's developing the game is a real dynamite guy, and I'm also told he's extremely handsome. The goal here is simply to move the red block into the yellow square hole as many times as you can, and you get bonus points for every blue block that you can beat. That sucked, but at least we've made some headway on the build, and we've barely made any progress. Let's just skip to the good part. That was fun. If you've been following along on your own dated machine and waited 30 minutes before getting to this point as well, you might hate to know that you could also install these binaries pre-built. Of course, you should be very hesitant to execute as root a shell script you got from the internet, or source code provided by a YouTube video for that matter, unless you know exactly what's going on in those scripts. If you're not familiar with Bash, or Linux in general, you could learn the basics with today's sponsor, boot.dev. If social media has whittled your attention span down to a crippling degree, but you still want to learn fundamental software skills, boot.dev strives to help you attain these skills by gamifying the learning process. Learning is a time-consuming and arduous grind. But you know what else is a time-consuming and arduous grind? An RPG. But that didn't stop me from putting hundreds of hours into open-world Dark Souls, anime Dark Souls, Japanese Deus Ex, and Deus Yellow. Imagine if those hundreds of hours were instead put into, well, literally anything else. Like using GitHub Actions for CI/CD workflows, or building an HTTP server, or, well, learning Linux. Boot.dev turns courses on these and several other topics into highly interactive RPG quests, giving you XP and achievements which can help you fight bosses. Or get a boss. Go to boot.dev and use the promo code SHEEFification, or click the link in the description below to get 25% off your first payment, even if it's for the annual plan. Thank you so much to boot.dev for sponsoring this video. Anyway, let's get back to compiling our LLVM-IR. Compiling our LLVM-IR into an executable takes a few steps, and accordingly requires a few binaries provided by our build of LLVM. You might think this is a deficiency of LLVM, but it's just that most compiled languages hide all of the compilation steps from you, and chances are they're probably using these LLVM binaries under the hood. As an optional 0th step, we can run our source code through opt, which will try to optimize our program for a generic target architecture. The optimization levels for opt are the same as you would expect from GCC or Clang. The first real step of compilation is the actual compilation. This is done with the LLVM compiler LLC. We can also specify an optimization level for LLC, which will enable it to try and optimize the source code for your specific target architecture. Now we have an assembly object, but we won't be able to run anything until we resolve those undefined functions I declared. So the last step is to link these declarations to actual implementations. We do so with LLVM's linker LLD. Well, you can't use LLD like that. It doesn't magically know where these functions are. Actual definitions of these functions can be found in libc. This is why these functions might sound familiar to you even if you didn't use LLVM before. We can tell LLD to link to libc by passing the LC flag. Or at least we could if the linker magically knew where libc was. But we can just provide that information too. Once LLD has access to libc, it can finally resolve all of the symbols. Or can it? Main isn't actually the entry point of a program. By default, the linker assumes that the program will start at a symbol called _start. By the time you get to the actual main function, a lot that you normally take for granted has to happen, such as setting up the stack and frame pointers and some other stuff you probably don't want to think about in general. So where is the start symbol defined? Well, the C runtime, of course. Finally, a successful build. Now, if we pass an integer, say like 15, we get what we expect. A segmentation fault. If you dig into the executable, you'll notice that it still has undefined symbols, even though all of these are found in libc. This comes from the fact that I'm linking libc dynamically, which means that the symbols I'm using that libc provides are not baked into the final executable. Instead, the linker expects that these symbols will be loaded whenever the executable runs. But who's supposed to be doing this dynamic linking if not the linker? That's right, we also have to name drop a dynamic linker which will be responsible for this stuff later. Now with our dynamically linkable executable, we find that 15 squared is indeed 225. Any questions? Okay. One at a time, please. But G, the file type of the resulting executable mentions the word interpreter. Does this mean LLVM is an interpreted language? Well, no. Even if you compiled the equivalent C program, you would get the same file description. Well, LLVM does provide an interpreter that runs the IR directly, though this is usually also done with a JIT compiler unless you force its hand. But gee, this program does not actually behave as you promised. If I pass the non-negative integer 18,446,743,073,709,551,616, I should get 0, but the binary prints out 1. Yeah, you're right. This is a consequence of stir_tool, clamping values that exceed an unsigned long rather than wrapping. But gee, given that you rely on both libc and the C runtime, how can you say that you are using a completely different language when you're basically just using C++? Okay. I see I have succeeded in making everyone equally upset, but since we can't get anywhere with all of you whining like this, let's not stand on the shoulders of C then, eh? First things first, we'll need to write our own runtime. Specifically, we need our own _start symbol, which will be responsible for calling the main function. Since the main function is expecting argc and argv, we have to figure out where these things actually come from. This means it's time to read the ABI. Specifically, figure 3.9 on page 29 tells us what we need to know. The stack pointer register RSP is initialized with a pointer to a 64-bit integer telling us the number of command line arguments the program was invoked with. This is our argc. This pointer also marks the beginning of our stack, but that doesn't really matter for us right now. Sitting above argc is the array of pointers to null-terminated command line argument strings. That is, the elements of argv. In pseudo-C, this means that we get argc by dereferencing the stack pointer and argv by bumping the stack pointer up by 8 bytes. That's great, but it's not obvious how LLVM can access raw x86 registers. Well, assembly can obviously do it, so I gotta find a way to harness its power.
And I think I found a way.
That's right, we're gonna cheat.
We can just sprinkle in a bit of x86 assembly in line, which copies the stack pointer into an LLVM IR value. You might find the notation easier to unpack if I used Intel's notation instead, but I get my groceries from TNT. The first string is the assembly instruction itself, which I'll get back to. The second string describes how the assembly instructions interact with LLVM. This is a comma-separated list of value constraints corresponding to $0, $1, $2, etc., respectively. For $0, we have the constraint equals $r. The equal sign tells us that $0 is an output, and the $r tells us that $0 is a register, which the compiler can choose on its own. This output parameter is eventually passed to the return value argc. For $1, we have RSP in curly braces. The lack of an equal sign tells us that $1 is an input, and the actual constraint tells us that $1 is given exactly by the register RSP. Now, since this is an input constraint, LLVM expects that it's actually going to be passed as an argument to this assembly block, in parentheses. Given that the whole point of this instruction is to read what's already in RSP, we pass undef to indicate that the value is undefined by us. But gee, I hear you say, why not just put RSP in the assembly string instead of putting that weird undef there? Absolutely not. Even if this may work by accident, you're asking for trouble. The compiler has no idea that you're using the RSP register at all when you write this. Although compilers can generate assembly, they ironically can't read inline assembly at all. To show how much it matters that you do it right, let's go on a short tangent. Suppose you're in a situation where you want to check if some 64-bit input x is equal to 42, and completely unrelated, you also need to invoke some crazy intrinsic instruction napu727, which does some super specific and performant thing that you just need. You read the documentation for napu727, and as a precondition, it requires that the RDI register is 0 for it to behave correctly. If you were writing this in LLVM with inline assembly, you might be tempted to write it out like this, where you zero out RDI as required with an explicit assembly instruction. If you compile this function and call it with x equals 42, you may be surprised to find out that the function actually returns false. If you're absolutely metal, you can probably guess what's going wrong. We're butting heads with the System 5 ABI. Specifically, page 20 tells us that RDI is used to pass the first integer argument to a function. In our case, this means that x is stored in RDI. As a programmer in a higher level language LLVM, we shouldn't need to be privy to the calling conventions of our system, even if we're trying to inject some inline assembly. We need to tell the compiler we're playing with RDI so it can work around us. Given the little I've shown you about inline assembly, the idea you might have is to specify RDI as an output register and pass it 0. When you plug in 42 for x in this case, you do indeed get true. However, you might notice something is missing from the assembly. Where's our nopu727? Well, all we told the compiler was that the assembly produces a value stored in RDI, which we intend to use, but then we go ahead and not use it. Besides generating a value, the compiler assumes that the inline assembly has no other side effects, and we didn't specify otherwise. So the compiler decides it's safe to completely remove this assembly since we don't use the output value either. Given that nopu727 is supposed to represent an instruction with a super specific and performant effect, we could fix this by telling the compiler that, actually, the assembly does have side effects. Now, we still get the correct return value for all x, but nopu727 is also called. Indeed, looking at our assembly, we can see that x, which is originally an RDI, mind you, is moved into racks before any of our inline assembly comes in. Anyway, this wraps up the tangent we've been going on, but I know the x86 cognoscenti among you are losing your minds a bit.
Gee,
And there it is. Using a move instruction to clear a register is suboptimal. What the Metallica fans are referring to is a particular kind of peephole optimization. When you want to set a register to 0, rather than doing the intuitive thing and, well, move 0 into the register, the better thing to do is instead to XOR the register with itself. Why, oh why would you do that, you may be wondering? Well, the reason is instruction encoding. The move instruction takes 8 bytes to encode, half of which is just used to encode the 0 itself. On the other hand, XORing RDI with itself only takes 3 bytes, largely because we don't need to encode an immediate integer in the instruction. Here's the thing though. Not having to remember counterintuitive gimmicks like this is exactly why I'm using a compiled language in the first place. But wait, not even this XOR is optimal for clearing RDI. Yeah, that's right. The real winner, coming in at only 2 bytes, goes to XORing EDI with itself. For those who don't know, EDI is a subregister of RDI consisting of its lowest 32 bits. So why would clearing the bottom 32 bits be enough to clear the entire RDI register? Well, obviously it's because the instructions on 32-bit subregisters automatically zero out the higher 32 bits. And since that's true, then surely we can go even further and just XOR DI with itself, right? No. Not only does the 16-bit variant take 3 bytes instead of 2 to encode, it doesn't even clear the high bits of RDI. So consistent and very cool, right? As a compiler engineer myself, I feel obliged to generally discourage using inline assembly as much as you can anyway. I understand that sometimes it's unavoidable, but the compiler really is trying to help you out for the most part. And yes, I am biased. To support my point a bit, there is one last trick we can apply to our toy example to use the compiler as much as we can while still invoking that nopu727 instruction. We can just invoke nopu727 by itself, and then pass 0 to it through RDI as an argument. In this form, the onus is no longer on me to clear RDI as efficiently as possible, and indeed, when you look at the generated assembly, lo and behold, we get the 2-byte instruction that zeroes out RDI. Where were we again? Right, we're trying to load argc. Since argv sits 8 bytes higher, we can do a similar thing, right? 开玩笑. The move instruction dereferences RSP plus 8, but we just want the value RSP plus 8. The most natural way to do this would be to write assembly like this. However, I can already feel the agitation of the bare metal ladies, because they know that there is an x86 instruction designed specifically for loading an effective address, like the address of argv that we're looking for. But how am I supposed to know that? We can extract argc and argv using essentially no inline assembly at all. The only thing we really needed the inline assembly for is to access the RSP register, but after that, we can load addresses and compute effective addresses all using pure LLVM-IR, and then we can finally call main. When we compile this code stub, we can see that the compiler does indeed generate the optimal assembly. Hang on. Why are we pushing racks onto the stack? The problem here is that LLVM assumes that this function may be called by some other function. Since registers are global, this means that LLVM generates boilerplate for saving and restoring the state of the calling function. To stop LLVM from generating all of this unnecessary fluff, we just need to mark start to be naked. Once we do that, we can see that all the boilerplate involving racks disappears. Now we've finally reached a point where we can call main. Well, almost. The System 5 ABI recommends on the top of page 30 that we also clear the base pointer, but we know how to zero registers at this point. Okay, we're almost completely done with the start function. All that's left to do is handle how the start function ends. The return value for main is the exit code that the process should terminate with, but that doesn't happen magically. Now that we're writing start, we're responsible for actually terminating the program and providing the correct exit code ourselves. So how do we do this? With the exit system call, of course. System calls are just functions provided by the kernel to allow a program in user space to do privileged things in a controlled manner. Since this is platform specific, there's no native way to do it, meaning we're back to writing inline assembly. I wonder when I'll ever actually talk about LLVM-IR itself. Anyway, 64-bit x86 has a syscall instruction which does exactly what we want. All we have to do is set up our registers correctly before invoking the instruction. Particularly, we put the syscall code into racks. Then, any parameters for the system call are passed in order to RDI, RSI, RDX, R10, R8, then R9. Yeah, I didn't get that wrong. Once the system call completes, the return value is put into racks. Oh, also, the ABI tells us that the system calls destroy RCX and R11. Destroy? Why destroy? Anyway, we can wrap all of this documentation into an actual LLVM function, so I don't have to think about it afterwards. There's nothing new here, except that to indicate that RCX and R11 are destroyed, we use a tilde prefixed clobber constraint. Anyway, now that we can make system calls from LLVM, we can write a wrapper for the exit system call. For reference, the table of system calls can be found at x64.syscall.shell. For example, we can see that exit is system call 60, and it takes the program exit code as its only argument. For good hygiene, I'll also put the halt instruction after, but this shouldn't be necessary. Et voici a complete start entry point which wraps around main. Well, now we've literally just got underscore started, but we have other libc dependencies that we need to eliminate. For printing output, we can just rely on the write system call. The system call technically returns the number of bytes written, but just like any good dev, I'm going to assume that the full writes will always succeed. With that, all that really remains is converting an integer to and from a string of bytes. Finally, I can actually talk about LLVM-IR. You might think that there's nothing really to talk about anymore since the language itself is quite simple, but there's one tiny little thing that makes it really special. Variables in LLVM-IR are static single assignment values. In non-compilerese, this means that every variable in LLVM-IR is const. This hasn't bitten us yet, but how are we supposed to write loops? Well, although LLVM values aren't mutable, memory addresses certainly are. This means one way to work around this constraint is to allocate our mutable variables onto the stack and then mutate the bytes on the stack instead. However, if we compile this into assembly, we'll see that we get exactly what we asked for. Unnecessary stack interactions. Well, I mean, this is assuming you don't run opt. The thing is, we're not supposed to write LLVM-IR like this. I mean, what are we, a language front end? The real way to deal with values that change are with fee nodes. A fee node is a magical pseudo instruction that selects a value based on which basic block you're jumping in from. In this example, which computes the nth sum of squares, we have a main loop, which we either enter from the entry block or iteratively from the end of the loop block itself. We can use fee nodes to track the index k and the total sum through this loop. Specifically, when we enter the loop from the entry block, the fee nodes initialize k to 1 and the sum to 0. However, when we return to the top of the loop from the bottom, the fee node instead updates k to be what used to be k.next and updates the sum similarly. In this way, the fee nodes encode the evolution of k and the sum without violating static single assignment. Here we eliminate the unnecessary stack usage for our integer parser by using fee nodes. All that remains now is to print the final integer without printf. This isn't too bad. The only annoying thing is that converting a byte-encoded integer into decimal is usually done from the least significant digit upward by taking repeated remainders modulo 10. Luckily, it occurred to me in a dream that a 64-bit integer has at most 20 digits. Accounting for the newline character at the end, this means that we can get away with allocating 21 bytes from the stack and populating this chunk with decimal digits in reverse before writing all of the bytes through a syscall. Now, after this whole marathon of cutting off libc, we can finally patch up our main function and we now have a library-free implementation of our squaring program. Now that we have no external dependencies, our resulting binary is statically linked and no longer reliant on a dynamic linker. This makes our compilation so much easier to instrument. Also, since we implemented the integer parsing logic ourselves, it also behaves exactly correct. If you're still here, thank you for watching. If you liked what you watched, then let me know, because this means I have failed in making everyone equally unhappy. If you didn't like what you watched, then mission accomplished. Regardless though, the null check on the number of fans who've got my back is something the compiler can always optimize away.